Burger, both from the University of Munster, and with Ville Kolemainen, who is at the University of Eastern Finland in Kuopio. And let me start by pointing out that what I am going to tell you today actually is just the latest chapter of a story that actually started with the plain problem of denoising an RGB image some years ago. And well, a little more than 3 years ago, I had the really great opportunity to give a talk here at this very same place about color Bregman TV. And since the model I'm going to present here today directly builds upon ideas that were developed in that context, I would like to start my talk today with a very short flashback on what this color Bregman TV was about and how this relates to what I'm going to tell you today. Okay, so let's consider admittedly very simple RGB signal in 1D, and let's add some heavy noise. So this is what we get. And if we then apply the very famous Houdin-Osher-Fatemi model introduced in the early 90s to each channel separately, then this is the characteristic result we can obtain. And as we can see, as you all know, the noise is reduced effectively, and the result still remains sharp edges. However, we can also observe that the position of the edges among different channels is not at the same position, leading to a slightly blurry impression of the result. And moreover, we also can observe a reduced contrast. So here it's not that extreme, but we can see that here the contrast is less than it is here, and the same for the other channels. Okay, and in order to overcome this last well-known problem, Osher and co-workers proposed the use of Bregman iterations in 2005, and indeed this approach then iteratively is able to restore the lost contrast. However, we can see here that the position of the edges did not change by that procedure. Instead, we just increased the contrast, and therefore this blurry impression seems to be even amplified. Okay, and against that backdrop, we then thought about how to maybe generalize these Bregman iterations to overcome that problem. And we did that in the following way. So we replaced the Bregman distance, which we have down here, and which is with respect to the previous iterate of the same channel, by a weighted sum of Bregman iterations to the previous iterates of all channels, leading to a joint subgradient, or in other words, to a joint gradient sparsity, and as such promoting or aligning edges, and it aligns their position and also the direction of the edges. Okay? Okay, and so this worked out quite nicely, and then at this point we ask ourselves, okay, so what might happen if we then somehow change the direction of one channel somehow to the opposite? Okay, so if we flip that red channel here, for example, and look at this signal, what happens? And indeed, we had to observe that the result we obtained with this color Bregman TV was not convincing. Thus, we already back then proposed to use the infinite convolution of Bregman distances, and this time with respect to all the previous iterates of the other channels and to their negative counterparts, and to apply this infinite convolution of those Bregman distances, and this indeed solves the problem. Okay, and then this did not only work for such a really very simple example, but also for a slightly more complicated instance. So here again we have a noisy two-channel signal, and then if we apply the Bregman iterations to each channel separately, this is the result we obtain. And if we instead apply this ICBTV-Regularisation, this is the result we can get. So edges are aligned, and also opposing edges are allowed. Okay, and in the meantime, we continued to work on that story somehow, and we even applied this model to joint reconstruction of PET-MRI data. And my colleague, Julian Rasch, worked a lot on a deeper understanding and a more thorough analysis of this ICBTV regularization. And so these results, and also like what he did in that area, well, he put that in there is a paper which is accepted in the Inverse Problems journal, so, and I hope that it will appear soon. And just for completeness, so no, sorry, what we mean by JTV here, what we refer to, is work by Eldar Taber and co-workers, and this LPLS refers to the linear parallel level set approach by Matthias Erhardt and co-workers. Okay, but this is not what I want to concentrate on today. This is just what I would like to give you somehow as a background where we came from. However, today I would like to move onwards to dynamic MRI applications, and I would like to discuss how this ICBTV regularization can then help to improve somehow the quality of reconstructions in this context. Okay, and therefore, as was announced in the, we would like to consider fMRI, and therefore I will give a short introduction to that, and use that to motivate our novel approach towards reconstruction of such data, and then introduce a mathematical model, show some corresponding results, and give a short summary in the end. Okay, so first question, why do we need brain imaging at all? Okay, the human brain consists of about 10 to the power of 11 neurons, and to about approximately 10 to the power of 15 synapses. And as such, this is still a highly complex system, and well, I think it still works in a miraculous way. So it's really, I think, so far it's unmatched, it's unbeaten, as Eldar pointed out this morning. Okay, and therefore, well, it will take another couple of decades before a realistic model and corresponding simulations might be available, if ever at all. We don't know. We don't know yet. Okay, and till then, neurologists will have to build their research on the nowadays available snapshots of the human brain structures and their function. And so this is what we need brain imaging for, to obtain such snapshots. Okay, and functional magnetic resonance imaging then is such a mean of obtaining such images, and it is a non-invasive imaging technique to depict physiological function inside the body, and thereby it aims at the generation of a map of the brain, as well as the identification and characterization of indicators of psychiatric diseases, such as, for example, Alzheimer's disease. Okay, and of course, I mean, it's already in the name, it is based on magnetic resonance imaging, and I think we all know that this comes along with a very good soft tissue contrast and a very high spatial resolution. Okay. And then the question was, okay, how does fMRI actually work? So there is put an external stimulus to the patient or proband, and this prompts a neural activity, leading to an increased metabolism, and therefore leading to local changes of the relative concentration of oxygenated and deoxygenated blood. And this then somehow leads to detectable local changes of the T2 star weighted MR signal in time. Okay, and this overall process is called or referred to as a hemodynamic response. And this figure somehow illustrates that. So here we have the neuronal activity, and then due to this change of the concentration of oxygenated and deoxygenated blood, the T2 weighted MR signal first increases and then decreases again. And this is different in every pixel somehow, in every location that we can measure of the brain. Okay, and let me already point out, well, at this early point, that this hemodynamic response seems to be a smooth process. Okay? Okay, and then what does such an fMRI experiment typically look like? And this is what really motivated us. So basically, the first step always is an anatomical high-resolution T1 rated MR scan. And then after that, the actual fMRI scan takes place, where these two T2 star weighted MR signals or data is measured over time, and in order to do that fast enough to depict such dynamic changes, we need some subsampling. Okay. And here I would like to just really say that for the anatomical high-resolution T1 scan, basically we can take as much time as we need, and therefore there we can really obtain a high resolution. okay? Because it's just taken before the actual experiment takes place. Okay, and after that, then the data after the data has been acquired, there is taken place some post-processing, and afterwards there always needs to be a statistical analysis. But what we are going to concentrate on, well, today actually is this data acquisition, and then we somehow propose a new model for reconstructing that data and getting images from that. Somehow the idea was to provide the to provide better results for the statistical analysis as an input data. Sorry, that was not possible to pronounce for me. Okay, so these were our key observations. So on the one hand, the high-resolution T1 rated anatomical MRI image and the subsampled T2 star rated MR images taken over time share many edges, because basically they just depict different features of the same underlying structures of the brain. Okay, this is the first observation. And the second one is, as I said before, that the evolution of the T2 star rated MR signal seems to be smooth over time. And therefore our question was whether we could improve the reconstruction of fMRI data by taking advantage of those observations. Okay, and well, considering these observations, we also had two considerations, so two ideas, and this is why I gave you this flashback in the beginning. So the infinite convolution of TV Bregman distances has been proven in different applications as an effective tool to promote a joint edge set between different image channels, even in the situation of opposing contrasts. Okay, and moreover, random subsampling in connection with a suitable regularization over time led to promising results in dynamic CT reconstruction, and there is a paper by Lena Frerking and Andreas Hauptmann and co-workers. Okay, and so now we thought, well, so let's just incorporate the additional a priori knowledge into a suitable variational model for enhanced reconstruction of fMRI data. Okay, and as I said, well, for the anatomical prior, for the pre-scan, we have a lot of time, so we take all the time we need to get a high-resolution image and sample the entire case space. And then the inverse Fourier transform gives us a really nice prior. So this is the anatomical T1 prior somehow. Okay, and now we would like to incorporate the edge information via the corresponding subgradient into our model. And formally, the total variation is given as this, as the one norm of the gradient, and then the corresponding subgradient, well, is given by this very line, and we can characterize this vector field Q, just by this equation. And then somehow this provides us with a kind of edge map, which is depicted like here, the subgradient. Okay, and well, if you look at this, you could maybe recognize that there seems to be some noise in the background, so we can also instead consider an artificial subgradient where we somehow just, well, remove the noise in the background by this eta here. So, but basically those are still, actually it works quite nicely with both approaches. This is just, some idea to make it even more, well, I think easier to, well, more intuitive somehow. Okay. Okay, so if we have this, then on the other hand, we wanted to take into account the smooth behavior of the hemodynamic response, and therefore we apply Tikhonov regularization over time somehow. Okay, and then our overall model can somehow be just built up out of those different building blocks. So first, we have a data fidelity, and well, we wanted to have something which is spatially piecewise constant, and therefore we added this total variation term. Okay, then we wanted to have similar structure as a prior, which we want to realize by this ICBTV regularization, and then we have some, well, regularity assumption in time, and since we said, okay, in this time the dynamics seem to be smooth, we did this with Tikhonov regularization. Okay, and then we first consider this simulated data set. So this is the sampling we took. We took 16 spokes per time step, and we chose them randomly. and this is the ground truth. Oh, sorry. This is the ground truth images at time steps 10, 17, 21, and 30. And this is then the full sampling of the anatomical prior, and this is the prior we obtained and we used for our somehow edge map. And what else can I say? Okay, maybe I should say that at this example, this prior did not have a higher resolution than, well, the sequence we took afterwards. This will be different in the second example I'm going to show. But usually this anatomical prior comes along with a higher resolution than the sample data. Okay, and so this is again the ground truth. And so there is a close-up here, and I'm not sure whether you can see it. So here, the middle of this area is a little darker, and then somehow it is filled, and it is getting out again. And what is typical about fMRI is that these dynamics are not very extreme. So it's not that you can see them extremely. And therefore I also plotted or used this illustration. So here you can see this is the original one, then it is somehow filled, and it is going down again. So it's okay. And if we then apply do some zero filling and apply the inverse Fourier transform to the data acquired in that way, well, above the upper line is the results we can get, and I think, well, you can't see much in those images. Okay, and then this is the reconstruction we obtained with our model, and let's now zoom in, and I'm again not completely sure whether you can here see how it's filled and getting out again. But so this is the ground truth and this is the reconstruction. And here you can again see how it's getting up and down again. Okay, and this is the ground truth and the reconstruction. And I'm hurrying up. This is temporal, like if you have a look at the time curves in an active pixel region and an inactive pixel region. And I hope that this convinces you that it works. And we also applied it to dynamic contrast enhanced MRI. And I'm going through this very, very quickly. And basically, it follows similar arguments. So again, we have the smooth dynamics, but this time the temporal data is T1 weighted. And then we thought, okay, as this worked out that nicely, we did only three spokes per time step, and then this is what we can get. And here, really, the prior had a higher resolution than the other one. And I hope that you can see that like this one really gives you, like, it is the same data that we used here. We just changed the reconstruction method, and I hope that you can really see how this increases the resolution. This is the time curves. And here again we have like a plot over the time, and I hope that you can really see that you can see a lot more results in with our new model. I think this already gives you quite a nice reconstruction, but here somehow the resolution is even higher. Okay, so the model we introduced, and we showed results for simulated fMRI and VLDC MRI data. And because of time restriction, I left out some or many of the mathematical rigorous results and arguments. But that can be looked up in the corresponding papers. And with that, I would like to thank you for your attention, and would be happy to take your questions or comments. Thanks.
Thank you. Just maybe one or two quick questions, and then there's also opportunity outside when there's a coffee break. So, maybe one.
Mm-hmm.
Is it really meaningful to synchronize the contours with the hemodynamic dynamic response? Are you sure that they will coincide? Here you promote the fact that the response
it
has similar boundaries with the anatomic brain.
Yeah.
It really sound from a physiological perspective?
I think it should be. So maybe if I just go back to these images, what actually happened there is so usually a special region of the brain is activated, and then in this region you can see somehow that the curve goes up and down, and but the overall structure of the entire, usually that only happens locally in the activated region, and the rest remains pretty much the same. And this infimum convolution of this ICBTV regularization does not really mean that edges, like if there is an edge in one channel, there does not necessarily have to be an edge also in the other. It just means that if there is some idea that there might be an edge, then they should be at the same position.
Well, this is the last one. Yeah.
Okay. Just actually, one two quick questions. Actually, fMRI data is actually typically acquired at a much lower resolution than you showed here. So what is done? Because this is rather high. I mean.
Yes. So like with this DCE MRI at least, there we at least had like with the anatomical prior, we had twice the resolution than with the fMRI data. And I mean, like here I would say the resolution is not very high, but from the data which accounts to this, we can really, with the anatomical prior, really can get this resolution. So I think it should, like here we really only took 3 spokes, so really a very, very low amount of data.
Okay.
So I think might work.
The second quick question which bothers me is it seems that actually the activation is assigned to the white matter area, which is the dark area in the T2 star area. What do you comment on that?
Well,
because that's an effect of debate, but I'm not sure whether it really existed. So
yeah, so actually I'm not that much into the biology or the behind fMRI. So therefore we just applied this, this was synthetic data which we somehow just created. But I think like this is real data, the DCE MRI, this is so therefore like I can't really tell you like whether this is a reasonable choice of an area to be activated. So we just chose an area, activated it. Probably, another area would be a more suitable choice. Thanks.
Yes, thank you, Maria. Almost.
Thank you.